record too. All right, one more time. This is what it should look like. The light color is from this top row. The dark color is the number in the second chart, and then out of the total. So 23, and then if you add these up, you get 131. So 23 out of 131. Same thing on the next one. But what I said is, again, make sure you label in your keys. Sometimes they count off for that, and sometimes they don't. So always put it just to make sure that you have it. So some of you just gave me the chart with no labels, no like the juice and proportion words. That all needs to be on there and a key. Does everybody understand? I didn't count anything off of it, but this is what you need to get full credit. Everybody got it? All right. So I want to show you too how they score it. It says it is essentially correct, which is your highest score, if the response correctly constructs and labels. So if you don't label it, but you make a great bar chart, you drop down here. You see what I'm saying? So that's the difference in a 4 and less. Got it?
Histograms are always important, aren't they?
No. Sometimes they're counts. Okay, frequencies and relative frequencies. It could be anything. Partially correct if the response fails to accurately construct a bar chart or uses frequencies instead of proportions. Some of you guys did that and didn't do proportions. And then incorrect if the response does not satisfy the criteria for E or P. So if you made this bar chart without the labels, you would get the P. If you didn't put any labels or anything on there and you did the bars wrong, you would just go down to I. Does everybody understand that? All right. So part B. Let me grab my paper out of here and then I'll start writing for you guys. Sorry. So part B says, assuming the conditions for inference have been met, you still have to do everything else. Okay, you still have to write your hypotheses and everything else. So some of you did not do that, which is fine on this one, because this is the one we're learning from, right? Okay, so assuming the conditions for inference have been met, does the coffee shop owner have sufficient evidence to conclude the distribution of sales is proportional to the number of facings at a 5% level of significance? Construct the appropriate statistical test to support your conclusion. So the first thing that you need if we're doing a statistical test, this is your 1.4, are your hypotheses. Some of you did this, most of you did not. So what are we trying to decide? What did it ask you? And I'm trying to leave this up here. If what? What do you mean? That they're equal. Or that they're not for the alternate. You could also show all the proportions. So mango was 18.75, orange was 0.250, and then your alternative would have been that at least one proportion was not specified. Okay, so I don't like that one. I like this one better because this is what you guys are used to. All right, so what are we going to do? And I talked to some of you about this. We're doing a chi-square goodness of fit. And I'm gonna give you a little bit of information here. Why are we doing it? Because a chi-square GOF test measures the difference between an observed and hypothesized distribution of categorical values.
Ms. Jones, when do you know to use a chi-square test and a goodness of fit test? Like, what's the difference?
Goodness of fit, categorical values. We'll talk about all of them throughout all of this. So what I would start probably doing is maybe keeping some note cards of each different test. Okay, so that you know exactly which one is what. For chi-square goodness of fit, realize this is not the chi-square test. This is the goodness of fit test. Your degrees of freedom are categories -1. Okay, so when we put this in our calculator, because this is all calculator, you don't have to do anything by hand at all. That's all in the calculator. But these are things that you need to know. So then in L1, you're going to put your second column, which is 23, 35, 46, so on and so forth. And in L2, the first one that you're going to put is 24.563. And the way that I got that was your proportion was 1875 and your total was 131 fruits. So remember, these are observed and expected. If you need to write that down, make sure you write that down. So L1 is your observed, L2 is your expected. And when you guys go in to your tests, it asks you L1 is observed, L2 is expected. So if you forget which one goes where, your chi-squared goodness of fit test tells you where it's going. Okay, so your observed is the 23, 35, 46. The next one is going to be 3275 because that is the proportion that you had in the first row times your total fruits. So on, so forth through that. You go to stat, test, chi-squared GOF. You have your L1 and L2 already in. Your degrees of freedom, there are 6 fruits, which would be 5. So I already have all of mine in to L1, sorry, ignore that. Into L1 and L2. Is everybody good? Expected, observed by multiplying these. And when you put these in, you don't have to find this value and then put it in. You can type it. I don't know if y'all know that, but you can just put in 0.1875 and 131, and it'll give you that value in there if I type it in right. Sorry. There you go. So you don't have to do it and then transfer it over, if that makes sense. All right. So then stat, test, chi-square, goodness of fit, enter, and calculate. If they ask you to draw it, you can draw it. Your calculator will do that. And then I would write down everything that you get. So I would even, y'all, I would write all this down just to have it. So your chi-square value was 10.46. Your p value, which a lot of you got incorrect, not a huge deal. Now you should know. And again, I already have degrees of freedom are 5, but it's not going to hurt me to put it again. Okay. Any questions on that so far? All right, so if we look at our scoring real fast, part B, you get it essentially correct if you have these 2 components. Your first component states the chi-square goodness of fit or correct hypothesis. So both of those will get you that full credit on there, the E. Partially correct if it's only 1 or 2, and then incorrect if it doesn't even tell you anything. Got that? All right. So then the next part asks you about, still in part B, asks you about the value of the chi-square, which is 1050 with a corresponding p-value of 0.06. So if you have the correct test statistic, did it say that you had to have all this chart that they have? Did it? No. And you have the correct p-value. Understand if you have the incorrect p-value, they will look at your work to see where you messed up, if that makes sense. Okay. So as long as you have those 2, you get the E for that. Got it? All right. Any questions on how I got that? All right. So then we need to conclude. How do we conclude? It's the same thing we've been doing for weeks and weeks. How do we conclude? And you did it, those of you that did the problem. Guys, come on. How do we conclude? Why do we get a p-value? Thank you. Yeah. We compare our p-value to alpha. Our p-value is 0.06. Our alpha is 0.05. Again, if they don't state it, use 0.05. If they do state it, whatever they state is what you want to use. We know that our p-value is greater than, so what do? What do we do? Fail to reject. Which means do not have. But there's a difference. Make sure it's in context of the problem. Okay. All right, so solution, the next one, scoring step 3, conclusion with justification. Since the p-value is greater than the level of significance, that's this part, you don't have to write that down. There is not sufficient evidence to reject the null hypothesis. This means that it cannot be concluded that the observed proportion of juice cells is different from the expected number of cells based on the number of facings. So just put it in context. It's the same thing we've been doing. So the only thing that I think you should have been confused on is which test to use. Okay, everything else should have been, I mean, we've been doing that for weeks. Is everybody good? So correct E if you compare the p-value to alpha, or fail to reject the null and states conclusion. So doing all three of this right here will get you full credit. Remember how I told you we were going to keep doing this over and over, because if you do what I tell you to, it's going to get you those scores, right? Okay, so make sure you have all those lists. Any question on that one? Is everybody okay with it now? All right, so that is 1.4. We'll jump to 1.7. Sorry, why is it doing that? Give me a minute, guys. Let me fix it. I think it's every time I touch the cord. I think I'm gonna use a different one. Give me a second. It's just me. All right. 1.7, number 1. This is probably the worst question on here because it's a lot of writing. The manufacturer of a certain type of new cell phone battery claims that the average lifespan of the battery is 500 charges. That is, the battery can be charged at least 500 times before failing. To investigate the claim, a consumer group will select a random sample of cell phones with the new battery and use phones through 500 charges of the battery. The proportion of batteries that fail to last through 500 charges will be recorded. The results will be used to construct a 95% confidence interval to estimate the proportion of all such batteries that fail to last through 500 charges. So explain in context what it means to be 95% confident. We've talked about this a lot. You gonna make it? All right. So this is their given answer. Let me just show you instead of writing it all down. And like I said, you guys can either write it all or whatever. Most of you had exactly what you needed. It just was a little less wordy than this is. All right, so this is what they have. If the consumer group selects many random samples of the same size of cell phone batteries and constructs a 95% confidence interval using each sample, that's the biggest part. Construct with each sample. Then about 95% of those intervals will capture the true population of all batteries of this type that fail to last through 500 charges. So just watch it and make sure that you do that. Constructs all the samples. Right. So most of you missed like that.
Like that last.
Right. Right. So that's, but still, you're on the right track, just add that extra in. So essentially correct if you mentions repeating sampling, so a lot of you did that. 95% or 95% of the corresponding intervals will capture the population proportion, and then describes the population proportion in context. So yours did not necessarily not get all three parts. Does that make sense? So that's all you need. Now to get your other one, it is partially correct if the response satisfies two of the three components. So you didn't, you know what I'm saying, just a little bit, always get that partial credit. Worst case, you got the P on here instead of the E. It's really simple. Got it? All right. So then part B said, suppose the consumer group conducts its investigation with a random sample of 5 cell phones with a new battery, and 1 battery out of the 5 fails to last through 500 charges. Verify all conditions for the inference for a 95% confidence interval for a population proportion. I swear, if y'all stop, please stop skipping this question. How many times have we checked conditions? Oh, a ton. And then the only thing that I'll tell you is if they ask you to check conditions, once one of them fails, you don't have to say, like the last one's going to fail. Okay, we already know that. You don't have to say that you have to graph it and there's strong skew or anything like that. It just wants those 3 conditions. Okay, so you don't have to say anything about the graphing. And I'm scared if you say anything about the graphing, they might be like, you know, it's wrong, it's messed up. Because I don't want you to say like the graph is skewed when it may not be. Does that make sense? And so if you say that it's a normal graph and it's a skewed graph, then they're going to mark the question wrong. Everybody understand? All right. So don't talk more than you need to. All right. So on this one, the first thing that we're going to check is that it's random. Is it random? What's it say? Random sample of 5, right?
We need to put like what the random sample would be.
I would.
Please.
I
So
would.
it's not just
If they're
say-
asking you to check conditions specifically, I would. If they're asking you to construct something, then it can just be stated and move on. All right, what's your next one? How do I do that? What was the number? 5, which is 50. This is what you need to start writing. Why is this okay? Assume the population is greater than 50. And then the last one, if you forget what it's called because you can't remember either one of them, that is fine. You can just write normal, okay? They will take that and that is perfectly fine. But remember, they gave us a proportion, okay? How do you know they gave us a proportion? 1 out of 5, okay? So if they give you a proportion, that's n p hat in 1 minus p hat. Your n was 5. Your p hat was 1/5 or 0.2, 1 out of 5 cell phones. So this gives you 1. The next one will be 5 and 4 out of 5, which gives you 4. Both are less than 10. So this one fails. That's all you got to have. Okay.
If you do the 10% rule and you don't need it, but they count that against you. Alright.
Because you're going to say that, assume the population is greater than blah, blah, blah. When do you not use the 10% rule?
When it's not a problem with examples.
When else? When we sample with what? Without replacement. Without replacement, because that changes the probability. So think about a deck of cards. If I pull a card out and I don't replace it, it changes the probability. It changes the number of the deck. Okay. All right. Essentially correct. If you verify the random sample, verify the 10% and provides evidence that either NP or N1 minus P is not met. Partially correct if you had 2 of the 3. So even if you screw up that last normal, we have done the first 2 forever, you get partial credit. Y'all understand what I'm saying? Pretty simple. It's not too bad. All right. The next part. Oh, it's at the bottom, sorry. Suppose a consumer group conducts this investigation with a random sample of 5 cell phones with the new battery, and 1 battery out of the 5 fails to last through 500 charges. Verify all conditions for inference, blah, blah, blah. For a 95% confidence interval for a population proportion to indicate where any condition has been met. In some studies, large sample sizes are not feasible because of the time and expense involved. However, small sample sizes can create issues with inference procedures. A simulation can be used to investigate what might happen with intervals constructed from a small sample size. Consider a population in which 30% of the population displays a certain characteristic. For each trial of the simulation, 5 observations are selected from the population and a sample proportion p hat is calculated, where p hat represents the proportion in the sample that display the characteristic. The following table shows the frequency distribution of p hat in the 1,000 trials. Also shown are the upper and lower endpoints of a 95% confidence created from the value of p hat using the formula blah, blah, blah. You already know that formula. For example, the sample of a 0.4 occurred 309 times in the 1,000 trials. So if you have a p hat or a proportion of 0, that happened 168 times, and your confidence interval would be 0 to 0. That's what it's saying, okay? 0.2 happened 360 times. This is your interval. So everybody got it? So if you didn't quite know how to read that, that's how you read it, all right? What was the question? Consider a population in which 30% of the population displays a certain characteristic for each trial of the simulation. For example, the portion. Does it even have a real question on there? Okay, so that's this. Oh, this one. This one's the next one. Yeah. We already did that question. Here, this one. Based on the simulation, blah, blah, blah. This is the answer that I just gave you, the conditions. Based on the simulation, what proportion of the 95% confidence intervals capture the population proportion for 30% or 0.3? Explain how you determined your answer. So explaining is not always writing words. Y'all understand that, right? It's not always writing words. It's kind of justification. All right. So if we look for 0.3, we don't have 0.3. We want to make an interval or values that capture 0.3. So we need to go lower than 0.3 and we need to go higher than 0.3 or that 30%. So on either side. So I'm going to write that down. We need to go lower than 0.3. And we're going to go down into that 0.2 category so that we make sure we capture everything. If we do 0.4, we're going to miss between 0.3 and 0.4. Does that make sense? But if we go down to 0.2, we're going to get all the 0.3s. It's going to be an overestimate, but it's better to overestimate than it is to underestimate. Okay. Lower than 0.3. And higher. Sorry, I can't see that. Yell at me next time. And higher than 0.3. And that's 0.3 from the beginning. Okay, so the 18642. So 0.3 from the beginning would be 0.7. All right. So then I lied to you. Ignore that I even said that. 0.3, we're looking for the intervals. Where is 0.3? Which intervals contain 0.3? Does the first one contain 0.3?
Yes.
Okay. Doesn't matter because it's 0. Does everybody understand that? What about the next one? Does it contain 0.3? Does the next one contain 0.3? Okay. So when we do this, what? Okay. So we're not going to include this one though, because it's that 0. The original is 0. So we're not.
Play nice.
I'm about to throw it across the room. Sorry, guys. I'm gonna get it in a minute. I think it's every time I touch the cord. Is it gonna work? Is it gonna work? I have another one back there. It'll be all right. There All right, we're gonna see how long this lasts. All right. So let me clarify this one more time. This is exactly what it says. To capture the true proportion of 0.3, the lower boundary must be less than 0.3 and the upper boundary must be greater than 0.3. Okay. This occurs for values of 0.2. So when we look back, at this, one more time, let me read it one more time. The lower boundary must be less than 0.3 and the upper boundary must be greater than 0.3. This occurs for values of 0.2, 0.4, and 0.6. 0.2, 0.4, and 0.6. Because those p-values occurred in 360, that's the number in the frequency. 309 and 133 trials. So that's a total of 802. We had 1,000 trials. So that's 80.2%. What box was I looking at? I was looking at the wrong table. That's why this is the table we should have been looking at. Which ones include 0.3? These include 0.3. Sorry, I was looking at your new table. Does everybody see that? That's where these three numbers, 360, 309, and 133 comes from. Is everybody good? All right, so 80% or 80.2%. If you also did, here's what it says. If you did 3 out of the total 6, you would get partial credit for that. So if you gave me 50%, because you didn't do the frequencies, you just did 3 of the intervals out of 6, you would get partial credit. Essentially correct explains that the interval captures the true proportion if it includes 0.30. You provide an answer of 80.2 and then includes justification by referencing to the appropriate values of p hat 0.2, 0.4, 0.6 explicitly or with clear reference to the table listing the actual intervals. So if you had 360, 309, and 133, that's your justification. Wes, you got all this? Mhm. All right, next question. That's all of that one. The next question. Sorry, I shouldn't have read on this chart. For sample sizes, small sample sizes, an alternate method of constructing a confidence interval is available. To implement this method, first include an additional 4 observations in the sample. So we're adding 4 observations, 2 successes, and 2 failures. Second, calculate a new sample proportion for the new sample. Finally, construct the confidence interval. For the cell phone batteries, consider a sample of 5 in which 1 battery fails to last through 500 charges. Using the alternate method described, what is the value of p hat new? Show your work. The following table shows the results of the original simulation with the revised 95% confidence intervals constructed with the alternative method. So if we look at this, we did have 1 in 5 that fails. So I'm gonna move it up so you can see it and try not to touch this cord. We had 1 in 5. We added how many failures? 2, yep. Remember we added 4 total, 2 were successes and 2 were failures. So how many did we add to the count? We added 4, which was 9. So this is 3 out of 9, which is 33%. Okay, look at these. Let me make sure I'm not skipping the next question. Trying to read it. Based on the results of the simulation, is the alternate method better than the traditional method described in Part B to construct a 95% confidence interval with a small sample size, and explain your reasoning? All right. So on this one, 0.33 is included in the original P chart of 0, 0.2, 0.4, and 0.6. That gave you 168 plus 360 plus 309 plus 133, which was 970 out of 1,000 or 97%. Remember, we were doing a 95% confidence. Which one is better, the original or the new? Perfect. So this one is closer to the 95%. Essentially correct if you calculate the new p-value or the new value of p hat with work shown. So that was that 33%. And then states that the alternative method works better because a greater proportion of intervals contain 30% and the value is closer to 95%. That's it. Okay. Any questions on that? All right, that's 1-7. Oh my gracious. I'm about to be real mad. Guaranteed this will not happen again. About to get the other one. Work. Yeah, Miss Walter opens those blinds all the time. And I want her to not. All right, sorry, y'all. Technical difficulties. All right. All right, 1.9, guys. All right, question 1. A team of psychologists studied the concept of visualization in basketball, blah, 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 blah. You guys did really well on this one. It says, based on the box plots, did basketball players who received visualization training tend to need fewer attempts to make 2 consecutive baskets from a distance of 22 feet than players who did not receive the training? Tell me what you guys said.
I said no because visualization has a knowledge where no.
Okay, what else could you have used? Cheese spread, what else could you use? What? Can you use the mean? Why the median? This is a box plot. Box plot does not tell you mean. Let me explain to you how the scoring works, okay? So let me go ahead and write this down. The visualized training has a median equal to 4, and then the not training has a median of 7. So what did you say? Fewer attempts, right? Perfect. That is the correct answer, 100%. Okay, 100% the correct answer. Let me tell you exactly what it says. When I find my paper. It is. Sorry, there's like 50 pages about how to grade it. All right. Essentially correct if the response satisfies the following 2 components: an indication that players who receive visualized training take fewer attempts before making 2 consecutive baskets than those who did not receive the training. A justification based on location, such as median of attempts is less than the group received visualization training, or that the number of attempts required was typically less for the group that received visualized training. It is partially correct if the response satisfies only one of the two components, and incorrect if the response does not meet the criteria for EP. To satisfy the second component, a response can compare the quartiles from the box plots, but should not compare the means, since the means cannot be determined from the box plots. So you would not get credit for using the word mean. So some of you did use that on your pre-response. Just make sure that you're talking about quartiles or medians. Range is still not even that great. So you might get credit. You might not get credit for that as well. It's got to be a specific location. So quartiles or medians. I would not use spread, but it is correct. It's just not what they're looking for. Okay. All right. The next part, state and check conditions for conducting a 2-sample t-test for a difference in means. What's your condition? Random. Was it random? Where does it say it? Randomly assigned to 2 groups. So it did random assignment. Okay. What comes next? 10%. What about this one? They picked 20. And you can do that, assume there's more than 200 basketball players, but we're not what? Yeah, we're not sampling. We're not sampling. So everybody is doing it. So we're not doing anything that we would need to justify the 10% rule for. Okay. So then the next part is normal. What do I do for this?
Numbers,
What are your group numbers? Remember, this is not proportion, right? So we're not doing NP. So what are we checking? That our numbers are greater than 30, right? What are our group numbers? 10 is less than 30. So it fails this. It doesn't ask you to make it normal or anything like that. Now, if it said, can we assume normality, continue on and try to graph it, okay? So essentially correct if you state and verify the random assignment condition has been met. Correctly states that the sample sizes are not large. Correctly states that sample distributions are skewed or refers to the outlier. We don't have any of that right now, or correctly states that the normal condition has not been met. Okay. Is everybody good? All right. Part C. Because both distributions, visualization and no visualizations are skewed. Did it tell you that before? No, but you can see them right here. After you go to this normal or whatever, because they gave you the charts or they gave you the box plots, go ahead and mention that this one has an outlier and they're a little bit skewed. Okay, so that's what it's saying. That would be your 4th component to get your E, because they gave you the box plot. On the other one, they didn't give you any charts. So they're not asking you to make one. Does that make sense? But this one, since they gave it to you, make sure that you talk about how this one has an outlier. All right. The psychologist conducted a simulation to test for a difference in medians rather than the means. For each trial of the simulation, the 20 values for the total number of attempts observed in the experiment were combined into one group and then randomly split into 2 groups of 10. The difference in the medians, V minus NV of the groups, was calculated for each trial. The following dot plot shows the difference in the medians for 100 trials with simulation. Using the observed difference in medians and the results of the simulation, estimate a p-value for the test of the difference in medians. Show the work needed to calculate this p-value. So what do you got to do? What are you looking for? The difference in what? So what was your medians? We got to do V minus NV. I already wrote it down one time. Your visualized training was 4. Your 9 was 7. And that's from the box plots on the previous page, which gives you what? -3. So the value is coming from there and less than, -3 and less than. Very good. All right, so how many dots do we have? Out of? $100? I told you that on the other page. I told you that on the other page. It's okay. It's okay. There's 0.17. The observed difference in medians from the box plots is 4 minus 7, which equals -3 attempts, because 17 of the 100 trials in the simulation produced a difference in medians of -3 or less. The estimated p-value based on the simulation is approximately 0.17. Essentially correct if the response indicates that the observed difference in medians is -3 and that there are 17 dots at -3 or lower, resulting in an approximate p-value of 17/100. Partially correct if the response uses -3, but not less than -3, which is what some of you did and got 0.04. So I did see some 0.04, so that's good. You're on the right track. Just make sure you do the less than as well. Or partially correct if the response indicates that the observed difference of means is 3. How would you get 3? Instead of -3. You reversed them. You see what I'm saying? And then you guys did this side. Does that make sense? Or maybe you even went from there down. All right. Partially correct if the response indicates the difference in means is -3 and count 17 dots at -3 or less. Does not give an estimate of the p-value. So you didn't go ahead and do the divide 100. All right. So then the last one, based on the p-value in part C, is there convincing statistical evidence that basketball players similar to the ones in this study who receive visualization training need fewer attempts to take 2 consecutive baskets? Blah, blah, blah. Just how you answer. How do you do that? Uh-huh. What was your p-value that you just found? 0.17. Alpha is 0.05. It's greater than, so fail to reject. H sub O, which means I cannot write today. Blah, blah, blah. So very good. So then, because the p-value of approximately 0.17 is greater than 0.05, that's exactly what we have. There is not convincing evidence that the players who receive visualization training take fewer attempts, blah, 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 blah. Essentially correct if you compare the p-value to the significance level, or states the p-value is not small, and states that there is not convincing evidence. And then provides context. So as long as you do this part and you write your sentence with, again, you just copy down what they wrote up here. You get a P if the response satisfies only 2 of the 3 components. So if you don't state it in context, you still get partial credit, but you got to say that we do not have convincing evidence. Okay. But if you don't write the rest, you still get partial. So if you're being a little bit lazy, and then incorrect if the response does not meet the criteria for E or P. So if you only get one of the parts, so you just compare this, you basically get a 0. That makes sense. Very good. All right. Any questions? That's the finish of 1.9. So 110, I think, has 3 questions, and we'll deal with that on Monday. I'm going to stop sharing, stop recording. You guys